This video tutorial is the second part of a three-part video series on geometric optics. The first one was about image formation by concave and convex mirrors. Today, I am going to discuss image formation by converging and diverging lenses. Before we look at the first problem, we will first discuss summary of sign conventions for thin lenses. If the focal length f is positive, the lens must be a converging lens. If the lens is diverging, the focal length small f is negative. For the distance object, we consider DO to be positive if the object is located to the left of the lens. Object distance is considered negative if the object is to the right of the lens. Now, for the image distance, it is considered positive if the image is formed to the right of the lens, where we say that the image is real. When the image distance is negative, then the image is formed to the left of the lens, where the image is considered virtual. For the magnification, it is denoted by small letter m. If the computed magnification m is positive, we say that the image is erect or upright. If the magnification small m is negative, then the image is said to be inverted. If the absolute value of the magnification is less than 1, then we say that the image is reduced in size. If the absolute value of the magnification is equal to 1, then the image must be of the same size as the object. And if the absolute value of the magnification is greater than 1, then the image is enlarged. All of these sign conventions are based on the assumption that the incident rays or the incoming rays are emanating from the left side of the lens. This is the first problem. A lens whose focal length is negative 60 centimeters is used to look at a duck 4 meters away. First question, where is the image located? Is it real or virtual? Question letter B, calculate its magnification. Is the image reduced or enlarged? Is it erect or inverted? So, first, let us identify the given data. Alright, so we are given the focal length, which is negative 60 centimeters. And earlier, we said that if the focal length is negative, then we say that the lens is considered a diverging lens. We are also given the object distance, meaning how far is the object located from the lens. It is 4 meters. And we are supposed to find the image distance, di. And based on the computed di, we are going to describe if the image is either real or virtual. Then we are also going to calculate for the magnification small m. And based on the computed magnification m, we will be able to determine if the image is either enlarged, reduced, or of the same size as the object. And finally, we will be able to determine also if the image is said to be erect or upright, or if it is inverted. Although you are not required, it is always better to first come up with a ray diagram, an illustration uh, of the situation, okay? And at the same time, this is also a method of determining the location of the image, all right? Making use of ray diagrams or light rays where we can, if this is done using the correct scale, okay, normally when used, all right, the ray diagram method requires us to have uh, the distance of the object, the focal length, as well as the image distance to be drawn following a certain scale. But just for purposes of comparing this, okay, with our computational procedure later, okay, uh, we are not going to follow specific scaling here. So, in other words, all the quantities here are not drawn to scale. Now, let's imagine that this is the lens, all right, located on this side. That is how we symbolize a diverging lens, also known as a concave lens. Notice that uh, the geometric center of this lens is thinner at its geometric center than at its edges. So that's one characteristic, the physical characteristic of diverging lens. That is, its geometric center is always thinner compared to the edges. All right, so it's just a symbol, all right, to represent diverging lens. So we draw also that vertical line, okay, to represent the surface or the what you call the middle or center of the lens. Okay, the center of the lens is represented by the vertical line drawn here. So we assume that all the incident rays coming from the object will be striking this particular vertical line. In other words, it's like saying that the incident rays coming from the object will be able to hit, okay, the lens before they get refracted. So, according to the problem, this particular lens has a focal length of negative 60 centimeters. By the way, a double diverging lens such as this has two foci. All right. The first focus is located to the right of the lens, and we normally call it the real focus. This is the real focus. And to the left of the lens, we also have the virtual focus, and the distance from that focus to the center of the lens is what we call the focal length. So we are given the focal length, which is negative 60 uh, centimeters. So the object is located uh, some 400 centimeters away from the lens. And as noted earlier, okay, based on our sign conventions, we will assume that the object is located to the left of the lens and that the incoming light rays will be coming from the left side of the lens. The lens is located to the right. That is our agreement. So, just like in the first video tutorial on image formation by mirrors, okay, how we are able to determine the image formed by lenses, okay, we make use of what we call incident rays, and we need at least two incident rays coming from the object. All right. The object, by the way, is represented by the red arrow, so that we will only be locating one point, and that is the tip of the arrow. Okay. Our task is to locate where the image of that tip of the arrow will be located. Okay. When refracted by the diverging lens. There is no need for us to locate the tail of this arrow because it is already drawn along the principal axis. Okay? So, I'm going to explain later as soon as we are able to locate the image of the tip of the arrow. Okay? What we mean by that. That there is no need to locate the tail of that uh, upright arrow representing the object. Okay? So, the first incident ray that we are going to choose out of the several possible incident rays that we can choose, okay, the most convenient one is to choose this light ray, which is parallel to the principal axis, right? That is parallel to the principal axis. When it hits the lens, it's going to be bent, all right, or refracted. Since it's a diverging lens, from the word diverging, that refracted ray will sort of diverge, all right? Meaning it sort of moves away from the principal axis, something like this. So that arrow represents the refracted ray of our first incident ray upon passing through the diverging lens. Now, we can trace or extend that refracted ray backward. Backward meaning uh, in front of the lens, something like this, but using broken line. And you will notice that the broken line passes through the virtual focus. Okay, that is the rule. If the incident ray is parallel to the principal axis, when refracted by the lens, it's going to pass, when extended backward, it's going to pass through the virtual focus. And that's what we actually did. We let it pass through the focus. Now, we need another incident ray, and this time we will choose a ray that is aimed at or towards the real focus. So to the right of the lens, we have there the real focus. And our second incident ray, the blue one, is aimed towards that focus. All right? It is only aimed or directed towards that focus. Okay, but it doesn't go through the lens and then hit that particular point we call the real focus, because exactly uh, at the lens, this is what's going to happen to that incident ray. It will be refracted such that it will become parallel to the principal axis. Okay, so we have chosen two incident rays. Okay, the first one, the red incident ray, that is parallel, initially parallel to the principal axis. Okay, when it is refracted by the lens, it's going to diverge such that when extended backward meaning uh, to the left of the lens, it's going to pass through the virtual focus. And we represent that using this broken line. Now, we need a second incident ray, and we choose the blue one. And the blue one is aimed at or directed towards the real focus, all right, which when refracted by the lens will become parallel to the principal axis. And when extended, just like in the first ray, the first refracted ray, when extended, okay, to the left, this is how the extended ray will be. There it is, all right. So notice that there is a point where the two refracted rays sort of intersect, and that is the point of intersection. All right? That exactly locates the image. All right? The image of the tip of the arrow that represents the object. And we draw an arrow that is, okay, that represents the image. And notice that that image is smaller in size. And not only that, it is also upright, okay, similar to the original object. How far it is from the lens, okay, we denote that with di, meaning uh, that is the image distance. If we did this following the correct scale, we can actually measure, okay, we can actually measure that image distance using a ruler, okay, and then use the scale that we actually choose. But since we did not, or I did not, okay, I did not draw this uh, whole thing using a specific scale. So we will just, okay, determine that image distance using mathematical computations. All right, and we will have that in the next slide. For our computations, we are given the focal length, which is negative 60 centimeters, converted to meters, that is equal to negative 0.60 meters. And the object distance is 4 meters. So we can actually determine the image distance using the what we call the thin lens equation, right? The thin lens equation is just the same as the mirror equation we had last time, which is in terms of finding the image distance, its original equation actually is 1 over di equals 1 over f minus 1 over do. But instead of using this reciprocal formula, we are going to use a shortcut formula. Shortcut in the sense that we are not going to deal with uh, reciprocals or fractions such as this one. All right. The shortcut formula is simply, that is for finding the image distance, is simply equal to or is di equals the product of do times f, okay, divided by the difference between the object distance and the focal length, or do minus f. So when we substitute the given object distance and the focal length, we have for the numerator 4.0 meters, that is to be multiplied by negative 0.60 meters, all over 4 meters minus the negative of 0.60 meters. Take note that the denominator, we have here a double negative, so that when we do our algebra, okay, our result for the image distance will be negative 0.52 meters. So that is the value of the image distance. Since it is negative, we say that indeed the image formed by the diverging lens is virtual. Okay, a negative di means that the image is virtual. Okay, and that simply means that the image is formed to the left of the diverging lens, and that agrees with the earlier ray diagram illustration. Now, uh, the next thing to calculate, of course, is we will find the magnification m using the formula negative di or negative quantity di over do. And substituting the value of the image distance, okay, we have negative quantity negative 0.52 meters divided by 4 meters. Then again, simplifying this, we will have our magnification, which is 0.13. The unit meter cancels out, and based on this computed magnification, which is okay a positive, all right, that's understood to be a positive magnification. Therefore, we say that the image is upright or erect. Okay, and since the absolute value of the magnification is less than 1, we say that the image is reduced in size, or it is smaller than the object. So all of these results do jibe with our result using the ray tracing diagram method. Our second problem, we have a 2 centimeter tall object placed 40.0 centimeters from a lens. The resulting image is 8.00 centimeters tall and upright relative to the object. Determine the focal length of the lens. Okay, so first, let's identify the given data. All right, so 2 centimeters here is said to be the height of the object, and we label that as h sub o. All right, and we are also given the height of the image, which is 8.00 centimeters. Now, it is given here that this image is upright or erect when compared to the actual object. Okay, so emphasize that here the image is upright, and we are asked to find or determine the focal length of the lens. So beforehand, we do not know if the lens is converging or diverging because it doesn't specify. But if you're going to analyze this given data carefully, right, uh, from the fact that the image form is said to be upright, all right, um, between diverging lens and a converging lens, which do you think can form an image that is upright? Well, the answer is both. Both a diverging lens and a converging lens can actually form an erect or an upright image. Now, if you're going to compare uh, the height, all right, the height here can also tells us about the size, okay, or the magnification of the image. Since the height or image height, that's hi, is greater than the height of the object, it is obvious that the image is bigger than the object. All right, and for an image that is enlarged and at the same time an image that is upright or erect, okay, uh, the only kind of or type of lens that can have those characteristics of an image is in fact a converging lens. So that is our prediction at this point. Now, the moment we are able to calculate for the focal length and it comes out that the focal length is positive, then that will confirm our prediction that the lens is a converging lens, right? We are asked to find, or we are required to find the focal length f. So we don't know what is the focal length. And to be able to calculate for the focal length, okay, we will use, as usual, the formula for determining the magnification first. All right, because we don't know yet what the image distance is. We cannot go directly to the formula of relating the focal length, the object distance, and the image distance, okay, because we don't know the image distance yet, but we do know the height of the image and the height of the object, and there's actually a relation between the magnification m to the ratio of the image height and the object height, and that is given in this equation. M is equal to, originally, all right, we say that the magnification is equal to the negative of quantity di over do, but that is also equal to the ratio of the image height over the object height. Notice that there is no negative sign, okay, for that ratio hi over ho. Okay, but we can use this since we know the value or the values of ho and hi. So let's determine the magnification, or we can actually go direct in finding the image distance. All we need to do is transpose the formula and isolate, okay, di, since we are looking for di, and that becomes di equals negative do multiplied by the ratio hi over ho. And substituting, this is what we will get. Di equals negative 40 centimeters. That is the object distance. And since, all right, in the formula, original formula for m, there is a negative sign. That is why we put here the negative sign as well. All right, negative 40 centimeters. Our object distance is in fact positive 40.0 centimeters. But when substituted in the formula, okay, there is that negative sign. So I emphasize that here, negative 40 centimeters, then multiplied by quantity 8.0 centimeters, the value of the image height, divided by the value of the object height, or 2 centimeters. And simplifying, we will get as the value for image distance, which is negative 160 centimeters. Right? So, a negative di, okay, actually means that the image is formed to the left of the lens. In other words, we have a virtual image. Question is, does a converging lens also form a virtual image? Okay, we can answer that by going to the calculation for the focal length, where the formula for focal length is using again a shortcut formula, product over sum, okay, meaning the product of the object distance by the image distance divided by their sum. And if we substitute, okay, since we already know the value of di, so we have 40.0 centimeters, which is the object distance, multiplied by negative 160 centimeters, which is the image distance. And then divide this by the difference, 40.0 centimeters, okay, supposed to be plus di, but since di is negative, therefore that becomes minus 1 over 60 centimeters. Again, doing your algebra, we will get, okay, the value for the focal length, which is positive 53.3 centimeters. So you see, our prediction earlier that the type of lens is in fact a converging lens, because a positive focal length corresponds to a converging lens. And if we are going to summarize the result that we got based on our computation, this converging lens, all right, formed a virtual image, all right, since our DI came out to be negative. Uh, Towards the end of this tutorial, we are going to give you the summary of uh, the different cases. Okay, the different cases. Actually, there are 6 cases for what we call converging lens. Okay, the different images and the different locations of the objects, as well as the location of the images in relation to the focal length. We will have that towards the end of this tutorial. Okay, so again, this is the result of our calculations and computations. So just like in our first example, I would like also to accompany this with a ray tracing diagram. So in the next slide, we are going to show how this situation, all right, can also be illustrated using a ray tracing diagram. All right, so supposing we have not done our computations yet, this is how you are going to come up with your ray diagram method. All right, so look at the symbol for a converging lens. You already assume that it's a converging lens. And unlike in example number 1, where we describe a diverging lens, this time we are talking about a converging lens. And if you notice, the optical center or the geometric center of this lens is thicker than its edges. That is the symbol for, okay, a converging lens. Okay, so we are also given the focal length already. Uh, we indicate here the focal length equals 53.3 centimeters. All right, and the distance of the object from that converging lens is also shown being equal to 40.0 centimeters. So the purpose for this ray diagram is just to, just like in the first example, just to show you how the ray tracing diagram can be done if, for example, you haven't done yet the computations. But since we already have done the computation and we were already able to calculate the focal length, so I just specified here what the focal length of this lens is, right? So we have here the what we call the virtual focus. Okay, to differentiate the virtual focus from the real focus, we use a what do you call this? F prime. Okay, we read this as F prime, meaning a virtual focus. F with no prime is the real focus. We have here the object. Okay, as is now, the object is assumed to be upright. Okay, and the size is as shown by the length of this arrow. Okay, in our problem, it was specified what, how many centimeters is the height of this object. All right, it was indicated. So just like in our first ray diagram earlier, we will choose the most convenient incident ray that will hit the lens, and that is a ray that is parallel to the principal axis. So there it is, parallel to principal axis. When it passes through a converging lens, all right, this is what will happen. The light ray, when refracted, will be refracted as if it passes through the real focus. All right. So the refracted ray passes through the real focus. There it is. And we can also extend it backward. We can extend that refracted ray backward using broken lines. And then we need another incident ray coming from the object, from the tip of that object. All right. But this time, okay, what we will do is we will assume that that incident ray is coming from the virtual focus. Okay, something like this. There it is. That blue arrow represents the second incident ray coming from the tip of the arrow that represents the object, and it's going to hit our lens, a converging lens. Okay, and when what do you call this? When extended backward using a broken line, it should pass through the virtual focus. All right. So this is another possible incident rays that we can choose, aside from choosing the one that is parallel. Okay. When it hits the lens, okay, this is what will happen to this incident ray. It will be refracted so that it becomes parallel to the principal axis. All right. And when extended backward using broken lines, we have here, okay, when extended backward, the blue broken line and the red broken line will meet or intersect at that point. And I'm sure you already know what that point of intersection represents. It represents the image. All right. So that image represents the image formed by the converging lens of this particular object. And as you can see, it's located far beyond one focal length. Okay, our focal length is about 53.3 centimeters, but it looks like that the image distance is much farther from the lens compared to the focal length. And in fact, we had that earlier in our computation. So this is just to show you how that particular problem, number 2, can also be represented using ray diagram or in a ray diagram or ray tracing. A method that you can also use. It's just that if you want to really calculate for the image distance is represented here. All right. Had you come up with correct scaling, okay, when you scale these quantities correctly, you could have determined the image distance simply by drawing and measuring using a ruler. Okay, but since we did not follow scaling here, okay, so we just relied on the result of our computation. But nevertheless, okay, this is how you are going to do the ray tracing diagram. So in the next, this once again confirms our descriptions of the image, right? Okay, based from the computation, we said that the object, that the image is still erect, all right, but it is virtual because it is formed to the left of the lens, or we can also say the image is formed on the same side as the object. A case wherein we say that the image is indeed a virtual image. Supposedly, this image, okay, the red arrow here, should be a broken arrow to indicate or to emphasize that it is not a real a real image. Instead, it is in fact a virtual image. So that's it. We will now proceed to the summary of the different cases in the next slide. All right, so this is now the summary. We have here in this table uh, the 6 cases when we are talking about image formation by converging lenses. All right, there are 6 cases: case 1, 2, 3, 4, 5, and 6. These are all for converging lenses. While for diverging lens, there's only one case. All right, so let's talk about the diverging lens first. This is the example that we had in our problem number 1. All right, so in that problem number 1, we have the object located in front of the lens, all right, at a finite distance in front of the lens, meaning to the left of the lens. And what did we get as a result in computing for the image? We found out that the image was formed also on the same side as the object, okay, is located. In other words, the image is located to the left also of the diverging lens. And we said that the image was virtual, all right? Also, the image was upright or erect, and it was reduced in size. Okay, so this is the case, the single case for diverging lens. So no matter what the focal length of a diverging lens is, all right, and no matter how far the object is from the lens, as long as it is at a finite distance and not at an infinite distance, we will only have one result, okay, for the image: virtual, erect, and reduced in size. Now, for converging lenses, uh, it is case 1, okay, that we had in problem number 2. All right, case 1, wherein the object was located at a distance lower than the focal length. Okay, that was the condition for the object. And we found out that the image, okay, was formed also on the same side as the object is, meaning to the left of the lens. The lens is a converging lens. Okay, that's why it was also described as a virtual image. Okay, and likewise, the image was erect or upright, and it was enlarged. So this was uh, illustrated in problem number 2. All the other cases, from case 2, case 3, case 4, case 5, case 6, there are also certain cases where there will be no image that will be formed, such as case 2. If the object is located exactly at the focus, okay, of a converging lens, there will be no distinct image. And the other case as well is case 6, where the object is at an infinity. Okay, at an infinity, the object, the image of that object will simply be formed exactly at the focus. It's just going to be a very bright spot. Okay, so no distinct image either. But all the rest, case 3, case 4, case 5, okay, there will be certain images formed, and most of the images formed by a converging lens are real, and they are inverted, okay, but they vary in terms of size. There are cases when, case 4, for example, where the image is of the same size as the object. All right. So probably you will notice that this summary for image formation applied to lenses are quite similar to those for mirrors. Try to check that, no, by comparing this summary to those of uh, convex and concave mirrors. They have a lot of similarities. So that will end our tutorial for this second part of a series of three uh, video tutorials. So one video tutorial coming up very soon. Thank you very much.